So, welcome to lecture series on advanced linear algebra. We have already defined in the inner product space the meaning of orthogonality of two vectors. Now, let me define today another terminology called orthogonal set of vectors. Let V be an inner product space IPS, that is inner product space, a set capital S of vectors in capital V is said to be orthogonal set of vectors provided every pair of vectors, every pair of distinct vectors in capital S is orthogonal. So, every pair of distinct vectors in S is orthogonal. So, that is the definition of a orthogonal set of vectors. Again, another terminology called a set of orthonormal vectors. A set of vectors in capital V is said to be orthonormal provided first S is an orthogonal set of vectors. Second, the norm of each vector alpha in capital S is 1. So, orthonormal set of vectors is basically orthogonal set of vectors along with the length of the or magnitude of each vector is 1. For example, consider over the Fn the capital S consisting of E1, E2, En, that is standard order basis on Fn, where Ei equal to 0, 0, 1, 0, 0, that is at ith place, at ith coordinate it is 1, otherwise 0 place. Then for standard inner product in Fn, we have inner product of Ej and Ek, this is equal to sigma xi and yi. Here xi equal to 0 for I not equal to j and 1 for I equal to j, and y I also is equal to 0 for I not equal to k and 1 for I equal to k. So, in this case we see that, so this implies that inner product of E j and E k equal to 0, and inner product of E j equal to 1. Similarly, over the let me consider vector space, let V be the space of all complex or real valued functions in the closed interval 1 which are also continuous. Consider inner product in V as inner product of f and g equal to 0 to 1, 0 to 1 f x g x bar dx. Now, with respect to this inner product, consider f n equal to root 2 cos 2 n pi x and g n equal to root 2 sin 2 n pi x. So, for n equal to 1, 2, 3 and so on please. Then the set capital S is equal to 1, f1, g1, f2, g2 and so on is a set of orthonormal vectors in capital V. So, this is a set of orthonormal vectors in V. How to prove it? We have inner products of say f n and g n. F n and g n, this is equal to 0 to 1 cos 2 n pi x root 2 and root 2 sin n pi 2 n pi x dx. Since it is a real, so bar is not necessary, not required please. Okay. So, this is equal to 0 to 1 to cos of 2 n pi x and sin of 2 n pi x dx. So, this is equal to 0 to 1, this is 2 sin A sin cos B. So, this will be equal to your sin of A plus B, that is 2 n plus 2 n, that is 4 n pi x, sin of 4 n pi x dx, because other one is sin A plus B plus sin A minus B, that is 2 n pi minus this both will 0. So, this is equal to like this. So, this is equal to, we will have cos of 4 pi n x by your 4 pi n 0 to 1, and this is equal to 0, because 4 pi n where n is positive integers. So, this is equal to, value will be equal to 1 and minus cos of 0 equal to also 1. So, that is why it is equal to 0. Similarly, we can check Fn Gm, which will be equal to there 0 to 1 to sin 2 m by x and cos of 2 n by x dx. So, again this can be simplified, this will be equal to your sin 2 into m plus n into pi x plus sin 2 into m minus n pi x. So, and dx from 0 to 1. So, if I integrate again, I will have this is equal to 0. So, if we consider any pair of distinct vectors, then we see the inner product equal to 0. Whether it is orthonormal or not, that we can again check, inner product of Fn and Fm. Inner product of Fn and Fn, that will be norm of Fn square, that is equal to 0 to 1 to cos of 2 n pi x square dx, please. This is equal to 0 to 1, we know cos square theta minus sin square theta equal to cos 2 theta. So, 2 cos square theta minus 1 sin square theta is 1 minus cos square theta. So, it is 2 cos square theta minus 1 is equal to cos 2 theta. So, 2 cos square theta is equal to 1 plus cos 2 theta. So, it will be 1 plus cos of 4 n pi x dx. Okay. This is equal to integration of 0 to 1 dx plus 0 to 1 cos of 4 n pi x dx. So, this is equal to 1 plus 0. So, this implies norm of Fn is equal to 1. We can also check norm of Gn also equal to 1. So, it is this implies the set capital S is equal to 1 F1 G1 F2 G2 so on is a set of orthonormal vectors also, orthonormal vectors. Now, let me prove one interesting results, that the set of orthogonal vectors is a linearly independent set. Let V be a inner product space, let S be an orthogonal set of vectors in V. Then S is also a linearly independent S is also linearly independent set. The proof is very simple. So, let us give a proof on these results. So, let S be a finite or infinite set of orthogonal vectors. Let alpha 1 to alpha n, alpha 1 to alpha n be a set of orthogonal vector. Claim alpha 1, alpha 2, alpha n is linearly independent. Let beta be a linear combination of alpha 1, alpha 2, alpha n. Beta equal to sigma C I alpha I, okay, I equal to 1 to n. So, I have taken a linear combination of this vector, this ones. I have to show that beta equal to 0 implies all C I equal to 0. We have inner product of beta and any alpha k for 1 less than or equal to k less than or equal to n, inner product of beta and alpha k equal to inner product of sigma C I alpha I equal to 1 to n and alpha k. So, this is equal to sigma C I inner product of alpha I and alpha k. This is equal to C 1 inner product of alpha 1 alpha k plus C 2 inner product of alpha 2 alpha k plus so on, and it will be C n alpha n and alpha k. So, this is equal to all are 0, this will be remain only C k and inner product of alpha k, because alpha I are orthogonal vectors. So, this implies that inner product of beta and alpha k equal to C k into norm of alpha k square. So, this implies C k equal to inner product of beta alpha k divided by norm of alpha k square. So, this implies the vector beta, which is a linear combination of alpha 1 to alpha n, is equal to nothing, it is the coefficient of in the linear combination can be written as beta and alpha k by norm of alpha k square and alpha k, k equal to 1 to n. So, this implies that beta can be written as linear combination of the alpha 1 to alpha k, and the coefficient of this alpha k is basically coming from the inner product of the beta alpha k by norm of alpha k square. So, this implies if beta equal to 0, if beta equal to 0 implies all inner product of beta alpha k will be equal to 0. So, this implies that all C k, which is equal to inner product of beta alpha k by norm of alpha k square, this will be equal to 0 then. Okay. So, the set alpha 1, alpha 2, alpha n is also a linearly independent set of inner product space V. Okay. So, every orthogonal set of vectors is also linearly independent. And not only that, interesting we see that any vector which is linear combination of the orthogonal vectors alpha 1 to alpha n, that coefficient of the each alpha k will basically inner product of beta that which is basically writing as linear combination of the alpha 1 to alpha k, the beta and alpha k by norm of alpha k square. So, now an interesting question is like this: suppose a linearly independent set of vector is given to us in an inner product space, is it possible to have corresponding orthogonal vectors? So, let me put this question in this theorem form like this. Let V be an inner product space and so let V be an inner product space and let beta 1, beta 2, beta n be any independent vectors in V, then one may construct orthogonal vectors such that for k equal to 1 to n, the set alpha 1, alpha 2, alpha k is a basis for the subspace spanned by beta 1, beta 2 and beta k. Also alpha 1 to alpha k is orthogonal set of vectors. Let me give the proof of this results. So, we shall prove this result by Gram-Schmidt orthogonalization procedure. It will be done inductively. Assume alpha 1, alpha 2, alpha m is already constructed, by the above procedure please, where m is 1 less than or equal to m less than n please. Of course, I have taken here alpha 1 equal to beta 1. So, now we shall construct alpha m plus 1. So, alpha 1 equal to beta 1 I have taken and assume that alpha 1, alpha 2, alpha m is already constructed, where m is basically lying between 1 to n, but strictly less than n. Now, we shall construct alpha m plus 1. alpha m plus 1 equal to beta m plus 1 minus inner product of beta m plus 1 alpha k and norm of alpha k square, then alpha k equal to 1 to m. We have taken alpha m plus 1 equal to like this. Here I can say certainly alpha m plus 1 not equal to 0. Otherwise, beta m plus 1 can be expressed as linear combination of beta 1 to beta m, which is not possible because beta m plus 1 beta m to beta 2 and beta 1 is a linearly independent set. So, therefore, beta m alpha m plus 1 cannot be equal to 0. Now, inner product of m plus 1 and alpha j, this is equal to your inner product of beta m plus 1 minus sigma inner product of beta m plus 1 and alpha k, that is your entire alpha m plus 1 and alpha j. So, k equal to 1 to m. This is equal to, by the property of the inner product, this is equal to inner product of beta m plus 1 and alpha j and minus sigma inner product of beta m plus 1 and alpha k. So, this is alpha k is missing, okay, and inner product of alpha k alpha j. Okay. So, it is like this. So, k equal to 1 to your 1 to m. Now, for k equal to 1 to m, inner product of alpha k and alpha j will be equal to, so this will be equal to this minus beta inner product of beta m plus 1, and when you multiply during the inner product with alpha j, except jth part all will be 0, and alpha j comma alpha j, inner product of alpha j comma inner product of alpha j will be there, otherwise it will be all at 0. So, here I have also dropped that norm of alpha k square is there, by norm of alpha k square please, okay, alpha j and norm of alpha j square divided by norm of alpha j square. So, this will be equal to inner product of beta m plus 1 and alpha j minus inner product of beta m plus 1 and alpha j, which is equal to 0. We see that if up to 1 to m, if this construction is met, then one can also do for the construction for the m plus 1 also. So, in this way one can go for up to m equal to n also. So, in this way one can have orthogonal set of vectors alpha 1, alpha 2, alpha n. So, one can have orthogonal set of vectors like this also by this procedure please. Let me take an examples. Let V is equal to our R3, I mean space of all 3 tuples with standard inner product in it. Let beta 1 equal to beta 1 equal to 304, beta 2 equal to like this, beta 3 this one. We can immediately check the set beta 1, beta 2, beta 3 is a linearly independent set. We can check it as a homework please. Now we have to obtain the corresponding orthogonal vectors please. So, by Gram-Schmidt orthogonalization procedure, alpha 1 equal to beta 1, that is equal to 304, and inner product of alpha 1 which is equal to 3 square plus 4 square which is equal to 25. So, for alpha 2 will be equal to beta 2 minus inner product of beta 2 and alpha 1 divided by alpha 1 norm of alpha 1 square into alpha 1. So, this is equal to minus 107 minus inner product of beta 2 and alpha 1. So, inner product of beta 2 and alpha 1 it is basically minus 3 plus 28. So, it is equal to 25. So, 25 by 25 into alpha 1, that is 304. So, this is equal to minus 4, 0 and 3. So, I see that alpha 2 is like this, where alpha 3 will be beta 3 minus inner product of beta 3 alpha 1 by norm of alpha 1 square and alpha 1 minus inner product of beta 3 and alpha 2 by norm of alpha 2 square and alpha 2. So, this will be equal to beta 3 is equal to 2, 9, 11 minus beta 3 into inner product of beta 3 and alpha 1. So, 2, 9, 11 and alpha 1 is 3, 0, 4 by 25 and alpha 1, that is fine, and then minus again inner product of 2, 9, 11, this alpha 2 is equal to minus 4, 0, 3, this divided by alpha 2 square. Alpha 2 square is equal to 16 plus 9, again 25 into your alpha 2. So, this can be calculated, it will be equal to your 2, 9, 11 and this will be 50. 50 by 25 into alpha 1. Alpha 1 is 304 and minus this is equal to 25. So, again minus only alpha 2 is equal to minus 403. So, if we simplify it, this will be equal to, okay, this is 0 and this side is 9 and this is equal to 0, okay. So, simply 9 and this is again 11, 8, 0. So, this is basically alpha 3. So, we have obtained alpha 1, alpha 2, alpha 3 by Gram Smith orthogonal procedure. We can check they are all orthogonal set of vector space. So, we will continue this concept in our next class.